Hernández titled The Visual World in the Dog Brain.
Okay, so I'm going to share my screen. There you go. Is it? Good. Okay, thank you for the introduction, Adam. So this is the name of my talk, The Visual World in the Dog Brain. So first, I would like to introduce you to my dog, Odin. Odin, it's a very interesting dog. He does very particular things. When he sees my cat, Cami, he has this very particular behavior. He stays really still. He tries not to look at the cat directly and not to make any sudden movements. In this way, he can stay for more time looking at the cat, so the cat doesn't get scared or he doesn't attack him. But he does something very different when he sees his friend Paula. When he sees Paula, he knows that it is time to play. So he tries to find a stick. He grabs the stick and takes the stick to Paula so she can play with him, talk. But it is different when he sees Rohan. Rohan is his dog friend. When he sees Rohan, he knows that it is time to play. So he goes to her, he tries to chase her, and they interact. Now, the thing is that in order for Odin to know what he has to do whenever he sees any of them, he needs to recognize them. So what we know is that the studies in the primate brain tell us that the visual information enters through the primary visual cortex, but then in order for the primate brain to recognize an object or to recognize something, it needs to process the information in the ventral temporal cortex. Now, when we look at the studies done in the carnivore brain, in particular, this is the example I'm showing you from the cat, we know that the primary visual cortex and the secondary visual cortex are similar. So these two are the same tissue. These two evolve in both species. But after the primates and the carnivores separated, the evolution took the visual pathway through different stages. And we don't know which region if there is a region in the carnivore brain that is similar to the temporal ventral cortex, or if there is a region that is encoding the information about the categories. So my question is, does the dog cortex possess an analogous region to the primate ventral temporal cortex? And in order for us to answer this, we train 12 dogs to remain still inside the scanner. We also scan 13 humans. So we were playing them videos of different things that I'm going to show you here. The videos are videos that, as you will see, they are moving, they are changing. You can see very different things going on in the environment and the different things that they are showing. But in general, they show you videos of cats, dogs, humans, and as a control, cars. Okay. So what we did then is that using representational similarity analysis, we took a portion of the human brain, a region that we know what it is doing. So we know that the early visual cortex is, I'm marking here the primary visual cortex. We know that it processes low-level visual information. So we took a sphere in the human brain, and we searched in the dog brain for regions that are performing a similar encoding than the human early visual cortex. But then, in order for us to find the ventral temporal cortex, we did the same. So we took spheres in the ventral temporal cortex, and we look at the patterns of activity of the human brain when they were looking at our stimuli, and search for these similar patterns, but in the brain. And this is what we found. So now I'm showing you here the overlap in orange. And in general, what we found is that the early visual cortex of both species seems to be the same as the previous studies are telling us. But in the case of the dog, the region that is encoding something similar as the ventral temporal cortex in human is more spread around the cortex. It's not focused in a particular region as the human brain, but it is also covering part of the early visual cortex. So our conclusion here is that the the primate brain seems to have evolved to have very separate regions that are performing different processes in general. But in the case of the dog, the cortex is not so specialized. Seems like these processes expand from the primary visual cortex, but they also cover other parts of the temporal ventral cortex. So that's it.
Great, thank you for that. Oh, I'm getting a little bit of feedback. Nope, now I'm not anymore. Okay. So that was a great talk. Very cute dog. We have plenty of time for questions. So if people want to ask a question or post in the chat, if you have any questions or comments, we have one question that's just come in. How did you search for a region? It seems to be too many degrees of freedom associated with such a process.
Yes. So what we do here is that we create the similarity matrix. So we take the processes, we compare how the brain is processing the different videos. We create this similarity matrix. The similarity matrix is telling you how different a particular brain region is processing a pair of stimuli. So we take all of our videos. We build this similarity matrix using the patterns of activity of the regions of interest, in this case of the primary visual cortex and also the ventral temporal cortex. We then search in the dog brain. Now the problem is that you might get many false positives. So in order for us to control this, we use permutation testing. So we repeat the same process, but relabeling all our stimuli prior to the analysis. And we build a distribution on how we expect, how many correlations we expect to find that are not really of interest, that are just noise. Yeah, and using this distribution, we can then find out if the correlations that we're finding are actually accurate. They are actually representing the stimuli. Yeah, have I answered your question?
Great. If you'd like more clarification, just post in the chat. So we have another question. We have several questions. So one question is the visual cortex ROI seems, and the human seems like it corresponds to peripheral rather than foveal vision. So what do we know anything about dog eccentricity? So like how dog's periphery might be represented differently.
No, actually, we don't have that many information in particular about dogs. There are studies that have looked at the visual pathway of cats, but they are invasive studies. In the case of dogs, this is a growing area. We expect to, in the future, be performing several other experiments in which we can look at particular details of the visual pathway.
Yeah, it would be really interesting to do like a retinotopic mapping study or something in the dogs, if possible. That would be I think very enlightening in how the visual system is organized.
Yeah.
Of course. So here's another question. Were you able to eye track the dogs to ensure that they were watching the videos?
Actually, the groups that have been studying dogs in the scanner, many of us have tried to use eye tracking. It's really hard to use it. The dogs don't have this white area in the eyes, so it's really hard to track what they are looking at. What we do here is that we put a camera outside the scanner, and the camera is looking at the face of the dog. So we just know whenever they are falling asleep or not. And after we take the scan, if the dog move a lot, we discard the scan. But in general, we know that they are looking because they have their eyes open.
Yeah, I'm very impressed that you're able to get your dog your dogs to stay still. My dog would certainly not be as compliant. So here's a question. What was the rationale for the choice of cars as your control stimulus?
We wanted something to which the dogs have some experience, an object that they have seen in their life, and also an object that moves. So we know that they have certain familiarity with cars, and they know that the cars move. So that was it.
Cool. So here's perhaps a slightly longer question. Since their category representation is spread out in more than in humans, do you think that dogs are slower at categorizing? So is the cortical spread going to indicate some kind of speed of processing? Is there any behavioral or neuroscientific study that might indicate how fast or even well dogs process different categories of stimuli?
That's a really interesting question. I don't know of any study that have make this comparison. It has many problems. One of them is that in order for you to ask a dog, you need to have certain paradigm in which the dog can answer. But then you will need to control how fast the dog can answer in comparison to a human. Another approach is to do it using EEG, and in the case of the group in which we are working here in Budapest, they are trying to do EEG with dogs processing different words. They can probably give an answer about this, but I will expect a very similar processing speed. I mean, it shouldn't really change that much. We're talking about 200, 300 milliseconds.
Cool. I'm going to ask a question, which is that that's kind of been hanging in my mind, which is that like you've only taken a very small region of human ventral temporal cortex or occipital temporal cortex, perhaps. But we know that for humans, there's quite a large spread, and the representational pattern that you're going to get really depends on where in ventral temporal cortex you sample, or whether you sample take, for example, the entire ventral temporal cortex as a single region. So my question is, how did you decide to put your ROI in a specific spot? And have you considered sampling more widely across human ventral temporal cortex to establish a representational pattern?
Yeah, that's a great question. I've been thinking of this like for over a year. So what I would like to do is like take every portion of the human brain and test it against every portion of the dog brain. And I actually tried several times of this. But if you think about it, the analysis is huge. I mean, if you take every single voxel, you will have millions of maps. I tried different approaches. I also use hierarchical. There is an analysis using functional connectivity that reduces the areas that you can use. So it creates like a mosaic on the brain. It splits the brain in different regions that are coordinated between them. So I try to use this. So I break the human brain in different parts, like in 200, 500 parts, and I try to search for regions in the dog brain. I couldn't find something really good, like something really consistent. So I stopped doing this. What I show you here is just like the tip of the iceberg of all the analysis that we did. But in just general, we choose these regions because they had the highest peaks when we use multivariate pattern classification. And we assume that, okay, so these are the regions that are performing better in the classification. So probably are the regions that have more information about the categories. But we also test some other things, like whether some dog regions have increased tuning against different categories of the stimuli, and other models, like a model from the primary visual cortex.
One potential way to do your results is actually to kind of flip it on its head, and rather than look for regions in the dog brain that show similar representation to the human brain, would be to look in the rather than look in the human brain and then try to find those representations in the dog brain, would be to like take parcels in the dog brain and try to find matching representations in the human brain, and then do a little bit of reverse inference there. I don't know if you've thought about that at all. but that could be
It's a good
interesting
idea.
too.
That's all, yeah.
Yeah, sorry, I didn't mean to cut you off, but it's been
No.
very interesting talk.
You.
We're gonna have to move on to our final talk of the session, but feel free to keep the conversation.